record on this computer. Hello, friends.
Hello, Mr.
Hello,
Stone.
Mr. Stone.
Hello, Mr. Stone.
I love it.
Hello, Mr. Stone.
Hey,
That
Gabe.
was the lamest hello, Mr. Stone ever.
There's the delay thing to it. Honestly, it's just nice to hear it every once in a while. Let's go over that angular momentum sheet, this week's practice sheet. Remember that angular momentum, L equals PR. So it's your regular linear momentum times the radius of the turn you make. And that's going to give you your angular momentum. The other way to find it is moment of inertia times angular velocity, which is way more comparable to the P equals mv. Well, what's the angular equivalent of everything? It would be moment of inertia instead of mass, and angular velocity instead of velocity. So that's a simple translation there. All right. Let's begin with this first one. A satellite is rotating once per minute. It has a moment of inertia of 10,000 kilogram meters squared. Aaron in mission control extends the satellite's solar panels, increasing its moment of inertia to 30,000 kilogram meters squared. How quickly is the satellite now rotating? All right. So moment of inertia is mass radius squared. But we don't need to find it. We've been given that, so we're good on that. We would use moment of inertia and angular velocity to find the angular momentum. Momentum is a conserved quantity, be it angular or linear, momentum is conserved. It's one of those things like energy or mass, where the universe has a certain amount of it and it doesn't get created or destroyed in any kind of interaction. So, unless a torque is applied to change the total amount of momentum, there won't be a change in the amount of momentum. So these satellite solar panels open up. One second. Drop my pen cap. All right. These satellite panels open up. The mass triples, or not the mass triples, the radius changes, causing this to triple. Sorry. All right, so the moment of inertia triples. This has to stay the same. So what must happen to our angular velocity?
It thirds. It goes down by a third.
Right, absolutely. So instead of having one rotation per minute, you would have 1/3 of a rotation per minute. So 1/3 RPM, or another way of saying that, same thing, just one rotation per 3 minutes. You might have phrased it either way. However, the important thing is that you're just going to cut the angular velocity down to 1/3 in order to make up for the fact that the moment of inertia has tripled. This is very similar to linear momentum problems where you have like sand falling out of the back of a train car with constant momentum. Well, it loses mass, so it speeds up or whatever. I start pushing a merry-go-round with a torque, lowercase tau, of 10 Newton meters. It has a moment of inertia of 100 kilogram meters squared. What's the rotational speed after 3 seconds, assuming it starts at rest? So these are all of the variables we're given there. That was an information-dense prompt. Well, let's see what we can do. This is kind of like those kinematic ones where you use FAM, Newton's second law. You use FAM to find acceleration from a force. And then you use the acceleration and a kinematic to find some other quantity. We'll also have that again later in this sheet. But in this case, we're going to use the torque and moment of inertia to find the angular acceleration. And then once we have that, we can use the angular acceleration to find how much our velocity changes. So this is a two-step problem. I suppose you could do it in one step if you substitute tau over I for alpha. You guys want to do that, or you want to do it as two steps?
2 steps.
2 steps it is. All right, so step 1 would be to use this formula to find the acceleration. We have 10 Newton meters of torque, and that is acting on something with 100 kilogram meters squared of moment of inertia. And that gives us our acceleration. One over 10 is 1/10. So our acceleration shall be 1/10 of a radian per second of speed gained per second spent torquing this merry-go-round. So that's the rate at which our speed is increasing. And then it's 3 seconds. Now you can answer this one of two ways. You can either you could count it on your fingers, or you could do it via math. But move that t to the other side, move omega initial to the other side, and you would arrive at this kinematic. Our final velocity is 0 plus 1/10 of a radian per second squared times 3 seconds. Boils and ghouls, what is our final velocity?
0.3.
3/10 or 0.3, depending on whether you prefer fractions or decimals. But 3/10 of a radian per second.
This problem is also kind of easy, like if you set it up like with Newton's second law, but momentum impulse.
Oh, like you did a moment of impulse.
Yeah, that's why I did it. Like torque times time equals like omega, or like change in omega times moment of inertia.
Absolutely. That's a really cool way to do that one. For anyone who is curious to see that, moment of impulse, that is the change in momentum, is torque times time. Now, the change in momentum could also be given as, I guess, that. So it's the impulse momentum theorem, but all angular, which is a pretty clever way to do it, because then you're going to get 100 times our change in velocity, which we're starting at 0, so we're adding our change to 0, equals 10 times 3. So we'd have 100 divided by 30. And moving this to the other side would be 1 over the change in velocity. Flip both. Our change in velocity is 3/10. Yeah, it works. It checks out. And it's 3/10 is the change from 0. That was slick. I like that. A comet is orbiting a star with only gravity acting upon it. In the video for you guys this week, I was talking about comets, how they're dirty snowballs in the outer solar system and they get pitched at the star by usually interacting with a giant planet. After a period of time, the star's radiation partially melts the comet. That's why comets begin to have those glowing tails. That's actually their atmosphere, which is, they're made of ice, right? So that ice melts and really sublimates into a gas. And then solar wind is blowing that gas off and also charging it electrically, so it turns into a plasma. So when you see a comet's tail, that only happens when it's near the sun. And that happens as a result of it losing mass. So it's not uncommon for radiation to partially melt a comet, decreasing its mass. The mass goes down to 1/4. But simultaneously, its highly elliptical orbit is causing its distance to the star to double. So this is a comet that's on the way out. So we have two changes that affect the moment of inertia. Now, a comet going around a star is a point mass removed by some distance r. For a point mass, your moment of inertia is mr squared. No need for a fraction if it's just a point mass. Like for a solid sphere, it's 2/5. For a spherical shell, like a ping pong ball, it's 2/3. And you don't have to take any sort of fraction with this moment of inertia. It's nice and simple. So we're cutting the mass down to 1/4 while the radius doubles. But remember, that radius is getting squared. 2 squared, 4. 1/4 is 1/4. So what's the overall change to our moment of inertia?
It's the same.
It's the ding dang same. So if our moment of inertia can't change and our angular momentum can't change, then what must our angular velocity do?
Also not change.
Also not change. So the angular velocity remains unchanged. So what is it in terms of its original condition? It's just omega. It was omega. It's still omega. It does not change in value because nothing else changed in value that it's related to. Or at least it didn't change overall. Any changes that were made canceled. Which is really neat. Consider a 30-kilogram disc. All right, have you considered that? You got that considered thoroughly? What is the moment of inertia of a disc? It'd be the same as it'd be for a cylinder.
Half mr squared.
1/2 mr squared is completely correct. And at a later time, we're going to drop a ring onto it. The moment of inertia for a ring, anyone got that?
Mr squared.
Just mr squared. All right. If you're given the name of a shape in an angular problem, then you need to just go ahead and be sure that you know how to find the moment of inertia for that shape. So that's the beginning there. But consider a 30-kilogram disc rotating with an angular speed of 12 radians per second. That's enough information to find its original angular velocity. Not angular velocity, angular momentum. Later time, we're going to drop this ring onto it, and then we're going to find a new angular speed. Well, remember that our momentum before is equal to our momentum after. However, afterwards, this momentum is having to spin more stuff, right? So if it's having to spin way more stuff, because this is another 15 kilos, and 14 centimeters wide, this is a heavy, big object, and the same momentum is having to spin all of that. What do you expect to happen to the speed?
Decrease.
Yeah, it should decrease. The same momentum having to haul more crap always causes the velocity to drop in order to compensate. So that's what we expect to happen. Let's make sure that that happens. Our momentum before is the moment of inertia of the disk before times the angular velocity of the disk before plus the nothing, because the ring is not contributing anything before. So it's kilogram meters per second. Kilogram meters squared per second is 0. And then afterwards, it is the sum of moments of inertia, because they're both being hauled together, times the final velocity. This is the same way you would do it if it was a linear momentum problem and you had two things crashing together and sticking. Well, this is, what kind of collision is this if when they collide, they stick?
Inelastic.
Inelastic. Very good. You guys do remember this stuff, or at least Robert does. 1/2 m. M is 30 kilos. R is 20 centimeters. So that is 0.2 meters squared. Don't make the same mistake I did like 5 times as I was like practicing this problem. I kept forgetting these squares. So in order to, maybe you underline it or something to emphasize it so you don't gloss over it. That plus 0 is just that, so I'm not going to write the plus 0. It's superfluous. The total moment of inertia is going to be that again. Oh, do you see what I did manage to forget? Well, I was telling you not to forget the square. What did I forget? You guys forgot it too, I guess.
You're 12.
The 12 radians per second needs to be multiplied by that. Luckily, I had enough room to write it on the other side. So 1/2 30 kilos times 0.2 meters squared plus 15 kilos times 0.14 meters squared times our final velocity we would like to know. All right, that is a lot, but we can do it.
Mr. Stone.
So
at the beginning of the moment of inertia lesson, we talked about how moment of inertia equals the sum of the mass times the radius squared.
mhm.
So can we just assume, since we know like the actual moment of inertia for each of these things, that we don't have to do that? Like what I did was I took the mass and the radius of each, and then like I didn't use the specific formulas for each one for that part of it to find the sum.
You'll be off by this half factor here.
Okay, so if we know what the formula is, just add them together.
Yes, if you're trying to add them together, because at first when I was reading this problem, I'm like, do I need to do this as linear and then convert? Because I have no idea what the moment of inertia for this combined shape would be. But then I realized this momentum is hauling these two objects with one velocity. So another way of writing this, you could write it like it was elastic. If they bounced, you would write it like this. And they've got the same velocity. Now, what would you do? Factor the velocity out, and then they just get added together. So do you see how that's equivalent to what we did?
Yeah, that makes sense.
Yeah, it's like how mass is additive in linear momentum, sort of.
Yep. So the total moment of inertia is getting hauled by this. Or you could always write it as the general L1 plus L2 plus L3 or equals L3 plus L4. And that'll always work for elastic or inelastic. It's just anytime that it is inelastic, you're going to have to factor out that final velocity anyway. But let's see. Let's actually do the problem. Hopefully everyone can see the calculator on their screen. 12 times 0.5 times 0.2 times 0.2 times 30. 7.2 kilogram meters squared per second equals 0.5 times 30 times 0.2 times 0.2. 0.6 plus 15 times 0.14 times 0.14, 0.294 kilogram meters squared per second. I guess that's just kilogram meters squared. Yeah, times our final velocity. Adding these together is going to be 0.894. So it should be 7.2 divided by 0.894 is our final velocity. 7.2 divided by answer. And I got, oh, wait, I screwed that up. 7.2. I thought my answer, I added them off the calculator. 7.2 divided by 0.894. Oh, that makes way more sense. 8 radians per second. So it slows down from 12 to 8. Which is what we originally kind of expected, that it's having to haul more stuff with the same momentum, so the total velocity ought to drop. It shouldn't be spinning as fast, and that's exactly what we found. Those conceptual checks like that will save your life. Please stop and think to yourself frequently, does this make sense? Not just in physics, but really in all aspects of your life, that should be a question you ask yourself. Do I need to buy this extended warranty? Does that make sense? All right. A car with wheels of mass 25 kilos and radius 0.25 meters is traveling at 50 meters per second. The car's velocity is 50 meters per second. Keep that in mind. So that is a translational velocity. Treating the wheels as disks of uniform mass density, that'd be 1/2 mr squared. That's odd. I mean, you'd think, well, no, because you got the hubcap, right? So like the wheel mount is where most of the weight of the tire is. So I guess they're ignoring the tire and they're more concerned about the hubcap, wheel mount onto the axle part. That makes sense. I'm so used to like bicycle wheels where we treat them as hoops and ignore the spokes. But calculate the angular momentum of just one wheel. Oh, thank God. That makes it way easier. So the mass is 25 kilos. The radius is 25 centimeters. And our velocity is 50 meters per second. Some of you would be tempted to make a mistake here. What is the relationship between mv and r when it comes to angular momentum? Well, if you watch the video, I gave you this derived form of it. L equals mvr. So you're thinking, all I have to do is multiply these guys together and I am done. L equals mvr works for a point mass. This is not a point mass. This has half the inertia, moment of inertia of a point mass. So what you could do, if you're feeling lazy, you could do mvr and then divide by 2. And I guarantee you'll get the same answer as doing this the longer way. But I'm going to do it the longer way first. Which would be this. Where omega is v over r.
Sorry, I don't know that one.
Everyone in my house is talking right now. L.
Sorry, I don't know that, but I do have a skill you might like. It's called my Talk 107.1. Want to try it?
No, thank you. Okay. So it's going to be 1/2 of 25 kilos times 0.25 meters, getting squared. Times 50 meters per second over 0.25 meters. And this will prove to you that L mvr divided by 2 would have worked. This gets rid of the r on the bottom. mvr, take half of it. Kind of neat. Not that you guys are easily impressed, but it's kind of neat. So we have 25. Half of 50 is 25. So we've got 25 times 25 divided, or times 0.25. So 25 times 25 times 0.25. 156.25 kilogram meters squared per second. All right, between the interruptions and also how I was kind of all over the place explaining an alternative way to do it while doing it a different way, everyone managed to follow that?
Yep.
All right.
Yeah, for the most part, yeah.
All right, well, that's all I can really ask for is the most part.
Well, you lost me for a second for some reason when you cut out the square, and it took me an embarrassingly long amount of time to realize it's because it was 0.25 that was being squared.
Yep.
I'm like, sorry.
It's all good. It would have probably been easier to follow if I had done all of my canceling out before plugging in, right? Like an r squared on the top and an r on the bottom. You would have followed probably more easily. Keep that in mind. Like those little ticks to your psychology as what makes stuff easier to follow. And then once you know what is easiest for you to follow, just do it that way all the time. And it'll prevent you from making the mistakes that you personally are prone to. A bowling ball. What kind of shape is a bowling ball? What kind of object? Is that a disc, a cylinder, a hoop?
Cube. A solid sphere.
Solid
A sphere.
sphere. And a solid sphere, it's not like a ping pong ball is a sphere, but all the mass is at the edge. This is a solid sphere. And a solid sphere has a moment of inertia of 2/5 that of a point mass. So it's going to be 2/5 mr squared. And it's traveling down a slope of 12 meters tall. So up here we've got our bowling ball. Down here we want to know what its linear velocity is. So this is our unknown. We know up here, it's starting from rest. So it has no initial kinetic energy. It has no initial speed to add to. So the only kind of energy it has up at the top is what?
Gravitational potential.
Gravitational potential energy. So up here, it's got mgh. That is 100% of our initial energy. But then down here, our final energy takes two forms: translational kinetic and rotational kinetic. However, these two must be equal to each other because, like momentum, energy is conserved. So we write this out as one big equation. mgh before is equal to 1/2 mv squared plus 1/2 I, moment of inertia, would be 2/5 mr squared. Omega, our angular velocity, which would be v over r, just so that we can keep it in the same terms, because after all, we're trying to find v, so who cares what omega is in and of itself? And then that gets squared. In order to prevent the same mistake of last time, like the r squaring being hard to follow, I'm going to do another step before I plug anything in. I'm going to distribute. mgh equals 1/2 mv squared plus 2/10 mr squared times v squared over r squared. And that's kind of neat. What is the significance of that? Think about that as like a generalizable principle. What just happened?
The
The
radius doesn't
matter.
affect the velocity.
The radius won't affect your velocity at the bottom of the ramp. Now check this out, because look here, mass, if we factor it out and then it's on the other side, cancels out too. So the radius doesn't affect your speed at the bottom of the ramp, and the mass doesn't affect your speed at the bottom of the ramp. The only thing that would affect your speed at the bottom of a ramp if you're rolling is the height, gravity, and the fraction that accompanied your shape. Right? So a ping pong ball versus a solid sphere would be a difference. But a ping pong ball of 1-inch diameter versus a 40-inch diameter ping pong ball, that wouldn't matter. Or even better, a plastic ping pong ball versus one made out of solid titanium. As long as it's still a spherical shell, there wouldn't be anything but a tie. Kind of neat. I mean, it's always important to pay attention to what cancels out, because that teaches you what is important for these scenarios. Just like Galileo, the big thing he found was that your mass does not affect your rate of fall. Well, this right here teaches us that mass doesn't affect your speed at the bottom of a ramp, and neither does the radius. The only thing that will matter is the distribution between those two, that shape, that fraction that comes with it. All right, so we have 2/10 v squared and 1/2 v squared. To come up with a common denominator, this should probably turn into tenths. So 5/10 plus 2/10. GH equals 7/10 v squared. 10/7 GH. Square root is v. So, square root of 10 times 9.8 times 12 divided by 7. And it is 12.96 meters per second at the bottom of the ramp. You probably got slightly over 13 if you use 10 for G, right? Like 13.0 something.
Wasn't this like identical to the one you did in the video?
Yeah, but it was a different ramp and I think it was a different radius
The
and
height was
mass.
different. The height was different.
The height was different. I think the mass and radius were also different. But the important thing there is that the mass and radius don't matter. So very similar to that one. But there were some superficial differences that didn't matter, and then one that did matter. I guess you could get different results by taking it to a different planet. However, the mass and radius still wouldn't matter there. You could plug in a different G on Mars, but that doesn't help you with these masses and radii canceling out. But yeah, this is very similar. You even get the same generalized formula for it. 10/7 GH square root is V. Like, we arrived at that in the video as well. However, in the video, it was also a bowling ball. It was a solid sphere. If it was a different kind of sphere, like a ping pong ball, a spherical shell, or if it was a hoop, this fraction here would change, but it would still be applied to GH and the square root would be taken.
Okay, sweet.
Yeah, so you'd have a different fraction GH, and then you'd take the square root of that.
Okay, that makes sense.
Yep, and you can just follow this process to figure out what that fraction would be. Next one, we've got a kind of a potter's wheel. We have a rotating disc, and it's going to get a blob of clay dropped onto it so that you can shape it into a, I don't know, flower pot or something. So we've got the scene from Ghost where Patrick Swayze's spirit is helping what's-her-face, at the pottery wheel. The disc has a mass of 2m. And remember, your momentum is going to be moment of inertia, angular velocity. And for a disk, it's going to be 1/2 mr squared omega. And in our case, we're starting out with 1/2 2 mr squared. The blob of clay gets dropped onto it. And I feel that it's safe to assume, like, if you imagine a blob of clay getting dropped onto something that's spinning, it's going to distribute by that centrifugal faux force effect. It's going to spread out. Kind of like when you spin pizza dough, it flattens out into a disc. So it shouldn't not be a disc, right? Like, we should still have 1/2 mr squared. It's going to be a disk with more mass. So it's going to go to be 1/2 3 mr squared, and then some new omega. Well, this has to stay the same, and our mass went up. By what factor? In other words, what do we multiply 2 by to get to the new one? What is the factor by which it changes? 2 multiplied by what gives you our new 3?
3/2.
I was going to say 1.5, but yeah, you're right. So 2 times 1.5 gives us this 3. In order to undo that, to keep L the same, we are going to have to take 1/1/5 times our angular stuff. because that would cancel out the change in order to keep our momentum constant. So our final velocity omega is omega naught divided by 1.5. Or if you did it with fractions like Riley did, that'd be 2 omega naught over 3, right?
Yeah, that's what I got.
So either one of those would be correct. Was that one followable? All right, go ahead and hit that thumbs up react so I can get a feel, even though some of you are being shy.
Where did the 1.5 come from again?
That was the factor of change. Like, if I told you it doubled, you'd know that the factor of change was 2. Well, it went from 2 to 3, so the factor of change was 1.5. Does that make sense?
Since it was a disk, though, like, wouldn't it, if originally before, like, the 1/2 and the 2 would cancel out, like your 1/2 from the formula for the moment of inertia would cancel out with the fact that it's got a mass of 2m.
Mm-hmm.
But then when we do like we did before, where you add them together, that would still cancel out. So you're adding what ends up being 1m plus another 1m from the blob of clay, and it ends up only being a 2m compared to the original 1. Does that make sense?
Well, let's see. If you wanted to do it that way, then it would have to be like this. It would be 1/2 m r squared omega naught equals 1/2, and that was 2m here. 1/2 2m r squared omega naught, or omega final rather, plus 1/2 m r squared omega final. So
why is it 1/2 for the last one though? Because Bob the clay would be a point mass, wouldn't it?
The clay is going to, when you drop a fluid onto, because the blob of clay we can assume is a fluid, right? It's in hydrostatic equilibrium if you have like no forces acting on it. But when you drop a blob of clay onto the potter's wheel, it spreads out and or at least it should try to. So I'm imagining the clay as flattening out into a disc as well.
Okay.
If you have the clay with, let's say you barely added any water to it and it maintains its integrity, then you would also need to know where it landed in terms of the radius of the turn. And we aren't given that information, so I'm choosing to ignore that information, right?
Okay, yeah, I just wasn't sure because it said on the edge, so I just kind of, in my mind, I went, oh, it clumped, but that makes sense too.
Well, if it's a point mass and it's at the edge, then we could do that as a second scenario. Do you want to do that one as a second scenario so we can like check your work, and that way, no matter which set of reasoning we follow, we'd have an answer.
Okay.
If we assume that it maintains its integrity and it can be treated as a point mass 1 radius away, then here would be our new equation. Now this is going to be kind of different. mr squared omega naught equals mr squared omega final mr squared, in which case mr squared is everywhere, and we would get this. So we'd just be adding the 2 omega finals because they're a like term. So if we follow the reasoning that it maintains its integrity, it does not flatten out into a disc like pizza dough because it is a thick lump of clay, and it lands right at the edge, in that case, omega naught is half of our final velocity. Or our final velocity, excuse me, is half of the original. So
All right, that's what I got. That's why I was asking, just to clarify on that.
right, you just had a different conceptual approach of like how it lands and hits. If it lands and it maintains its integrity and it doesn't flatten out and become distributed over the disk, then it should cut the speed in half. If it flattens out and distributes like spinning pizza dough to make your crust, in that case, you would have this. In order to avoid confusion, I hope that if you have something like this on the like AP exam, I hope that they're a little bit more specific. But there you go. There's two different approaches depending on a conceptual difference. All right, now a bowling ball of mass 5 kilograms. Bowling ball is a solid sphere. That's 2/5 I. And radius, blah, blah, blah. And we have the rotational kinetic energy. All right, we haven't started with that before. And we find its period. All right, so our rotational kinetic energy will be 1/2 moment of inertia, which is 2/5 5 kilograms, 0.12 meters. That gets squared times omega. Omega has within it the information we need. Why? Because what goes into finding omega? It's your displacement and your time. The period is the time to complete how many rotations?
1.
1. So 1 rotation in radians would be 2 pi. But keep in mind that is going to be a squared quantity because it's 1/2 moment of inertia velocity squared. So when we plug in, this is going to be 2/10 5 kilos, 0.12 meters squared times 2 pi over period, and that gets squared. Now, before we get a chance to forget these squares, let's distribute them. Also, that K is 20 joules. 2 times 5 is 10. 10 over 10 is 1. 0.12 times 0.12 would be 0.0144. Two squared is 4, pi squared is 5 pi squared. T squared is T squared. And again, this is done by plugging that in for our velocity. You could have just found the velocity as a number and then converted it for the time, which I know Riley Jeffries, you did that, right?
Yeah.
So you could just find a value for omega and let it ride from there. Like once you've got that, you use displacement over time and you plug in 1 revolution as the displacement. I like to make things unnecessarily complicated. So
Why did you put 2 pi over t for w? You cut out for me when you explained that.
Okay. This is your velocity, right? So if this is your velocity, it's displacement over time. Period is the time in 1 rotation, which is 2 pi radians.
Okay, I understand. All right, thank you.
No problem. All right, so just move that t squared to the other side. Pull the 20 joules down to this side. T squared is 0.0144 mass squared times 4 pi squared divided by 20 joules. Now it's calculator time. 0.0144 times 4 times pi squared. Damn, I've raised it too many powers. Please stop. Okay, there we go. Divided by 20. And then we have, now that's t squared is this. So we're going to take the square root of that. Square root of answer is 0.17 seconds. All right, I feel like that one, as soon as you like start actually plugging stuff in, wasn't that bad. It might be intimidating to set it up, but as soon as you get to here and you make this change, then you should have a vision to see the problem through the rest of the way. Oh, we lost somebody. Who'd we lose? Who'd we lose? I don't know. Two 1,500-kilogram cars are racing side by side on a perfectly circular racetrack. The inner car is 450 meters from the center of the track. The outer car is 452 meters from the center of the track. The outer car is moving at 20 times 10, 200 kilometers per hour. Determine its angular momentum. All right, I want you to envision this. You've got a car. Here's the center of the track. It goes around in this circle. There's no mass from the car to the center of the track. Therefore, what does that make this car? What are we modeling it as?
Hoop.
A hoop or a point mass. Luckily, there's no difference in the moment of inertia there. So this is a point mass. You could do mr squared, or because this is a point mass, you are allowed to use L equals mvr, which makes this one real fast. Our mass is 150 kilos. Our velocity is 200 kilometers per hour. Of course, that is not a base unit, so we need to put it into base units. There are 1,000 meters in 1 kilometer. And in 1 hour, there's 3,600 seconds. And our radius would be the distance to the center of the track, 452 meters. Just to make sure my units come out okay, get rid of like terms, meters per second. Okay, that'd be good. Calculate. 1,500 times 200 times 1,000 times 452 divided by 3,600. And we get an awfully large amount. But then again, this is a car moving in a big circle really fast, and it's also heavy. So having a large amount of momentum is not surprising. Our angular momentum shall be, I'm going to round it to 377. There's 1, 2, 3, 4, 5 zeros. Kilogram meters squared per second. This next one is easy for a couple of reasons. Let's start out with a basic question. Which of these cars is going faster? Your silence is telling. It tells me that you're either 1, shy, or 2, very learned, and you are waiting for more information before answering. And I'm going to choose to believe that it's the second one. You see, faster can be defined in one of two ways. Translational velocity or angular velocity. If these two things are going side by side so that they make the circle in the same amount of time, which one has the greater angular speed?
They're the same.
They'd be the same, because the angular speed is how fast you finish the circle. So one might be farther out, and they're going to have the same time taken to finish the circle. So there you go. Same angular speed. But which one is traveling faster translationally?
The outer one.
The outer one. So if we take L equals mvr, the outer one has a greater translational velocity and it has a greater radius. Therefore, it's got a greater angular momentum. Even if you ignored that there was a translational velocity difference, you still should have gotten this one just because the radius is bigger. Because if you use moment of inertia times angular velocity to find the angular momentum, well, the change in radius is squared. So a little change in radius is going to give a reasonably large difference in angular momentum. But then on top of that, there's a translational speed difference.
You could sort of think about it like that one demonstration you did where if you thought about like the other car just being moved to the same radius of the other car, if like its momentum was conserved, it would have to go faster. But in this
Okay.
example, like it would be slower.
Right. I dig it. Now, the drawing seems to indicate like downward motion, but it says right here, this is a horizontal tabletop. So this is spinning kind of horizontally. So imagine this like flat on the paper as opposed to the paper being like, this is up and this is the ground. And this is flat. This is on the plane of the paper. The nice thing about that is we don't have to worry about gravity. It's all flat and it's all on the ground. It's all on the flat plane downward. So there's no need to worry about gravity in this one, which is going to make it a lot easier. Otherwise, this is going to be like that centripetal force stuff where you're on like a roller coaster loop or whatever. But as it is, it's pretty easy. We have a rectangular rod, and it is spinning at a constant rate of 40 radians per second. It moves through here. Its length, I will have you notice, the length of the rod, how does that relate to the circle the rod would make?
It's radius.
The length of the rod is the radius of the turn. Please note that. I know like your initial suspicion in a question that has both length and radius as variables, your initial suspicion is, oh, I just cut the length in half and bam, radius. Well, in this one, the length of the rod is the radius of the turn. So be careful out there, kids. They're trying to sneak these past you. Don't fall for it. And the length of the rod is given to us as 15 centimeters. The mass of the rod is given as 0.52. And they even were kind enough to include the moment of inertia formula so that we don't have to derive it or find it or whatever. But this thing is spinning, so it picks up angular momentum. And then when it smacks this ball, and the ball scoots off this way with some translational velocity, so whatever angular momentum it has becomes the translational momentum the ball has. There's your equation. L before is going to turn into our momentum after. But how do we do that? Well, how do we turn L into P? We had a conversation about this a moment ago, Will. How do we turn L into P?
Divide by R.
There you go. That is our formula. We find the momentum the rod has before, the linear momentum it has before, and then we stick all of that momentum into the mass of the ball. And we'll know the velocity of the ball. So let's follow that. Momentum is going to be ml squared over 3. And that is times omega. And then on the bottom, because it's divided by 3, and also we're dividing by r, so we're going to stick an L on the bottom. That cancels, so that's not squared anymore. Then that is going to be equal to mass of the ball times the velocity of the ball. Now keep in mind, this is the mass of the rod, this is the mass of the ball. So those don't cancel. Don't cancel those out. You'd be getting overzealous if you tried that one. And then we just plug into this formula, and it is a quick calculator problem. Hell, if you want, you can already go ahead and move the mass of the ball over to this side, and you can do it in one swift step. So it'll be the mass of the rod, 0.2 kilos, times the length of the rod, 0.15 meters, times its speed, 40 radians per second, divided by 3 times the mass of the ball, which is 0.067 kilograms. We will have the velocity of the ball. A lot of moving parts there, yet you boil that down into the formula and it feels extremely doable. 0.2 times 0.15 times 40 divided by 3 times 0.067. About 6 meters per second. 5.97 meters per second. The lowest number of sig figs we have to work with is 1. So I think this should probably be rounded to 6 meters per second. I would have considered that one a pretty spicy medium. Not quite nightmare mode or anything, but definitely a reasonable amount of difficulty there because there were a whole bunch of parts moving around on it. Somebody just joined late. I'll go ahead and for the benefit of them.
It's me. I got kicked, so I came back. I'm good.
Oh, all right. Well, it's good to have you back. I was thinking, oh man, I need to put this key on Edsby now so that this person doesn't end up showing up and not having what they need. But then again, I'm putting this Zoom on YouTube, so I guess I'll need to put this on Edsby. Not that you guys are watching my YouTube videos. I see my number of views going down. I see none of y'all hitting the like and subscribe, buying merch in the store, and joining the Patreon.
If you sell a banana shirt, I'll buy it.
Actually, that's what my wife suggested. Like, we should do a Banana Friday class shirt.
Yeah, I'd buy it.
That's definitely a for real. I would buy that so quick.
Well, let's do this one, and then we'll plan shirts afterwards. A 5 kilogram weight on a rope is swung around at 1 revolution per second until it comes into contact with a resting kilogram brick on flat ground. The brick travels 10 meters. What is the coefficient of friction? Holy crap. We haven't had one of these in a while. You guys recognize this? This is the Batman problem.
Yeah.
The one where he swings down and tackles the Joker and they slide, and how far do they slide? This is that problem, but the swinging is happening horizontally. So it is a take on that. It's somewhere between that Batman problem and the one we just did. All right. So we have a 5 kilogram weight on a rope. That makes, unless this rope is extremely heavy, what does that make this weight?
Like 50 newtons, I think. About.
I mean, what does that make the object? We're treating it as
an elastic collision.
A point mass is what I was looking for, but yeah, this is going to be an elastic collision.
Oh, okay.
So this is a point mass. That's important because that allows us to find its moment of inertia. And then 1 revolution per second. Revolution is not a metric base unit, so we need to turn that into rads. So 1 revolution is 2 pi radians per second. So that is our speed. So we're going to do the exact same thing. The linear momentum before, which is found by taking the angular momentum and radius, is equal to the linear momentum after. So this is going to be I times omega divided by r. R is 1 meter. This is a point mass, so it's just going to be 5 kilos times 1 meter squared. That's easy. 5 times 1 is 1. So 5 kilogram meters squared times 2 pi radians per second. Yields. Radians aren't really a unit. Mass, meters goes away. So our linear momentum afterwards is 10 pi kilogram meters per second. Okay. What does that make the velocity of the brick afterwards? Well, it's a 1 kilogram brick. So this is equal to mv. This is a 1 kilogram brick, so this divided by 1 kilogram. The velocity that the brick starts to move at is 10 pi meters per second. But then it's going to decelerate. So that is our initial velocity of the brick, 10 pi meters per second. It stops at 0 meters per second, 10 meters away. That is enough to find the acceleration. If we find the acceleration, we know the force, because we can use FAM. And if we know the force, and we know that the force is friction, then we can use the normal force times mu, and we will finally have the coefficient of kinetic friction. Many steps, but none of them are hard. You just have to develop the vision to see all the way through to the end of the problem. That is where this problem gains its difficulty. Each step is easy, and it's stuff we do all the time. But to have to do 4 or 5 steps, and to also have the clarity of planning to see through all the way to the end of that 5-step plan, that is why this one is rough. Vf squared equals Vi squared plus 2a displacement. 0 equals 100 pi squared plus 20a. So negative 100 pi squared equals 20a. Thus, our acceleration is negative 5 pi squared. Whew. All right, we're almost to the end of this thing. To turn that into a force, we use Newton's second law. Multiply it by the mass of the brick. Thankfully, the mass of the brick is 1. 1 times 5 pi squared gives us a force of 5 pi squared newtons as the force of friction. Also, the force of friction is normal force mu. So that's going to be 1 kilogram weighing down with 9.8 meters per second squared as its gravitational acceleration. mg, its weight, is what normal force is equal to. So 9.8 newtons times mu. Five pi squared divided by 9.8. Well, pi squared is pretty close to 9.8 actually. 5 times pi squared divided by 9.8. And mu is just about 5. Remember, mu is unitless. It's just a ratio.
Yeah, pi squared is what, 9.85?
There you go. So this is an extremely sticky brick. Like, this is like oddly high for a coefficient of friction. Like, this is extremely high for a coefficient of friction. This would have to be
sticky brick.
This is like a brick covered in super glue that's dried a little bit, so it's really tacky. And maybe the brick is made out of copper and it's moving through a magnetic field, so there's also magnetic braking as well. Like, this is extremely high. This is wild, but it's what you get.
I got that answer and totally thought I did the problem wrong just because of how high that is.
Yeah, I actually, I was talking this over with Riley, and he had the same thing. Like, well, it couldn't be that one because that's physically, that's ridiculous. Yeah, the numbers are given. If you look, how many times was it, divided by 1 or times 1 in this problem? These numbers were not chosen because they're realistic. These numbers were chosen because they're easy to do without a calculator.
Hey, when I first did this, I accidentally did it as 1 radian per second instead, and you actually get something more realistic. You get 0.025.
Right? If they'd done it as 1 radian per second, this would have seemed way okay, they got a realistic answer. But no, they made
revolution. 1 revolution per second with that much weight on the end of that big of a rope is moving.
Yeah, this thing is if you imagine somebody swinging a sledgehammer with a meter-long handle, this is moving faster than a human being could reasonably swing it. So this is an insane amount of momentum being delivered. So yeah, it makes sense that this thing, if it's only sliding 10 meters after getting hit with that, then it's got to be pretty freaking sticky to stop it. So we've gotten to the end of the sheet and we're starting to lose participants. We've had 3 people sign off since we got to the end of that problem. So I guess you guys are ready to call it a day. After all, it has been quite a bit of time. It's 4:22 now. Oh, maybe that's why people were logging off. They got to 4:20 and had something better to do. Suspicious.
I like that.
Hey, this entire month is 420. Come on.
Well,
oh my God, you're right.
I should probably edit this discussion out before posting it on YouTube. All right, let's call it there. It's probably dinner time in your household.
So the shirts.
Oh, yeah,
yes, the most important part.
I think you should put boba on a banana.
A
Yes.
banana?
Yes.
A bow banana. A bananoba. A bonoba.
I think it would be really fun to do a take on North Korean propaganda and
Oh my gosh.
and
What?
have people marching and then the rising sun behind Kim Il Sung and then Just like
Stone, I will.
like
I will buy
really
that
like play that up and like
$50.
banandatory Friday.
Oh God.
I will buy that so
Oh,
fast,
God.
so quick.
Banandatory.
Okay, some of us are gonna be with you next year, so let's do it.
How did we go from boba on a banana to North Korean propaganda?
Same thing.
I'm always thinking about North Korean propaganda. You gotta realize that.
Mr. Stone,
This is a
where's
night
your
for us to workshop for sure.
do you have any Physics 2 classes before 4th period? You do, right?
I have no idea what my schedule for next year is. I know
I'm leaving after 4th period, and I want to take Physics 2. So I really hope.
I'm pretty sure I have an AP Physics before and after lunch again.
Okay.
So there should be one. A worst case scenario is you could sign up for AP Physics 2, and they would just create another section of it, and you'd be working by yourself in like an honors class.
Yeah.
So, your paper said that it was 3rd and 5th.
3rd and 5th? Okay. So there's
yeah,
3rd period.
wait, when is BC next or AB next year? Do you know?
4th.
Robert? Is it 4th? And
Yeah.
this is 3rd?
Yeah.
Yeah.
Okay.
Or, now hear me out on this.
I
If
hope
you
it's
want,
an econ for a second. Anyway.
hear me out on this. I know that my first period next year, and I think my second period as well, are honors. And honors covers some of the topics that get left out of AP 1 that are also on AP 2. For example, magnetism is not covered in AP 1 at all. It is in AP 2. But there is a magnetism unit in honors. So
Okay.
if you did get stuck in an honors class by yourself for AP2, that might not actually be that bad of a thing.
Although I am also kind of taking physics, well, because I'm taking physics with calculus. Well, I'm going to take 2 if I can. I think you have to get a 4 or 5 on the calc and physics exam. But if I do, I'll take AB calculus with physics 2. But if I don't, then I'll just take the first one. Because you can skip the first one if you've taken calculus and physics 1.
All right.
You can skip to the second one.
Well, I mean, whatever works for your schedule. It's I just show up and teach. I have no say.
I think you would have to have some of us in your honors class because they're considering the number of people that want to take it, yet the space in your class.
Yeah. Some people might get moved around. But a lot of people said that they wanted to take AP2, but I haven't seen like actual rosters for AP2. I know that I've got AP2 sections during both of my AP1s. But that's as far as my awareness goes. Like I haven't seen like a roster or whatever. Some of this stuff, if you guys are just trying to fill out your schedule and your senior year, you're looking more as like, hey, let me take it easy. I've been doing these AP classes for so long. Another option is if you've got 7th period free, I've got astronomy. And astronomy covers quite a bit of this stuff too, or at least builds off of a lot of this stuff. You've heard me use astronomy examples all the time in this class. So it would be a logical next step if you're just trying to flesh out.
That's what I should take over the summer.
Astronomy.
I've been thinking about something just to take over the summer, kind of like because why not? But nothing seemed like nothing seemed like it was fun enough to take, but also not like serious enough that I would want to wait till like my actual. Like I'm not going to take any of my core classes over the summer.
If I sign up for it, I'll let you know what my class code is, and we can hop in the same class.
Yeah, if you guys need any perspective or tutoring or whatever for astronomy, let me know. I've got a third of my life I spent teaching that class, so I'm reasonably well versed. Also, I think I wrote some of the final exam if you're taking it like through like Hillsborough County. I don't know how virtual school works, but
I take classes through HCC, so
that'd be different. The
Yeah.
HCC, because I've had kids come to me with the HCC astronomy stuff. It's way more like, how do I use the constellations to tell time versus how did planets form? Like, you see how there's a lot of different stuff under that astronomy umbrella. And the HCC one is way more like Boy Scouts astronomy, like
Boy Scouts astronomy.
as opposed to astrophysics, right? Like antique astronomy, where you're using it mostly to like navigate and know where you are on the planet and like what time of year it is, versus using it for astrophysics purposes. So we're talking like 1600s type astronomy versus post-Newton era astronomy. But either way, I can help you out with it. I know all that crap.
I'd be down for summer Zooms with Stone for astronomy.
Yes.
Well, then I'd be willing to do that. If you guys take Astro, I will support you. By the end of it, you'll just like look up in the sky and just know what time it is.
I'm excited for that.
I can
Like
do
I
that
have my
too.
phone.
There's a sun. I'm like, it's daytime.
No, I mean like, if you can see what phase the moon is in and where it is in the sky, you should be able to tell with like 15 minutes error what time it is on the clock. Like, it's actually pretty easy once you learn it. And you know what? There's great gizmos for that.
Yeah.
All right, guys, we have been on for an hour and a half. Let me go. And I'll
All right,
post-
Mr. Stone.
Yo, wait,
Bye,
is there a
Mr.
tiny
Stone.
quiz at midnight?
Yeah, then the tiny quiz drops at midnight as per the usual. And
Wait,
I,
there's one due at midnight?
No. I'm going to post it
Okay.
at midnight, and I'm going to leave it open. Since Monday is a non-school day, I'm going to leave it open, I guess, until Tuesday or something. Like, I'll leave it. I haven't done a good job of announcing it, so I'm just going to leave it up for a really long time, and we'll make it do Tuesday at midnight.
When is it on school day?
Okay.
Monday's a non-school day for like.
Although
the
that's
summer.
almost irrelevant at this point. Like,
Well, the difference is that I'm not allowed to give assignments that are due on a non-school day.
yeah, but I feel like I never have
Edsby
stuff
won't even
that's
let me
due.
put them in.
I always get stuff that's like due in a few days or in a week. So it's like I just have a week to do this number of assignments. So it's like
Right.
I always end up doing about the same number of work on the weekend as I do on the days.
Fair enough. All right, guys. Adios.
Have a good night, Mr. Stone.
See ya.
Later, team.